warm welcome to our scientific afternoon entitled Infrared Imaging Techniques for Cultural Heritage. It is my distinct pleasure to welcome and introduce Professor Fulvio Mercuri from the University of Rimu Tor Vergata. But before we proceed, I would like to thank also our Professor Mladen Franco, who actually brought this event to fruition. I will proceed with very short presentation of our guest. So, Professor Fulvio Mercuri is full professor of applied physics at the University of Rimu Tor Vergata, where he teaches general physics and applied physics of cultural heritage. He has been director of the study program in restoration of library materials and currently coordinates the laboratory of non-destructive and environmental analysis of cultural heritage at the Department of Industrial Engineering at the University of Tor Vergata. His research activity in the field of cultural heritage concerns the study of optothermal properties and deterioration processes of materials constituting artifacts of historical and artistic heritage, and the development of infrared-based methods for the non-destructive investigation of bronzes and books. Professor, over to you, please.
So can you hear me? Okay. So first of all, thank you, Professor Dobricic. Thank you, Professor Mladen Franco, and thank you all for this opportunity. It's a great pleasure for me to take part of this event, which is focused on a very, very fascinating field of cultural heritage, the one of the infrared imaging, for a huge number of different kinds of artifacts in the field of cultural heritage. So I want to tell you at the very beginning that I've structured my presentation, this lecture, in two parts. In the first one, I would like to recall the basic context of the infrared imaging for cultural heritage, and some information of the most common employed techniques for this kind of investigations. And in the second part, I will review some case study that have been selected because they will give me the opportunity to discuss with you, to present you some novel application that have been developed to solve specific problem in different field of the cultural heritage. And let's move to the very basic question: what infrared imaging is. To me, is the production of infrared images, is the production of images of an artifact as it would be seen by an infrared eye. We don't have infrared eyes, but we have infrared detectors, infrared cameras that provide us with a huge number of different possible infrared appearance of the artifact we are investigating, displaying elements, buried elements, subsurface features, elements that are not visible to the naked eye. And how can we do that? There is a large number of infrared imaging techniques, but essentially they can be classified into large category. One, which is the one referred to the so-called reflectography, and the second one, which can be referred to the thermography. I want to say only two words on the principle of those of those two kinds of technique. Reflectography, well, to explain what reflectography is, I think that most of you maybe already know it, but we have only to think to the mechanism of the natural vision. You have an artifact, you irradiate it with visible light. Some part of this light is backscattered, reflected. It's essentially a reflection process. It is collected by a visible detector that generates pictures, photograms, and this is the basic principle of photography. Exactly the same mechanism, you can translate it into the infrared region of the spectrum, and you have an artifact that is irradiated by infrared radiation, part is backscattered, reflected, and then there is an infrared detector generating infrared reflectographic images that we will call reflectograms. As far as it concerns thermography, the situation is a little bit different. I think it's very different. We have two kinds of radiation, so we can irradiate our artifact with light, with visible radiation, which is selectively absorbed by different part of the artifact, and these stimulate the infrared emission that is collected by an infrared camera, usually, which is a device for this purpose, generating infrared thermographic images that we will call thermograms. So in short, the main difference in between those two categories of technique is that reflectography can work with just one kind of radiation. Thermography can work, or better, this kind of thermography that I'm going to show you, that will be called pulsed thermography. This kind of thermography works with two different kinds of radiation. The first one is for the stimulus of the artifact. The second one is for the generation of the infrared images. When I should use one or I should the other one, it depends on the characteristic of the artifact you want to investigate. But there is one characteristic which is the most important one, and it is the opacity of the artifact. This is what I'm going to say can be trivial, but it is better to say it. If we have an opaque material like this one, this is a bronze statue, actually the images that you generate, that you produce, they are produced with the radiation, infrared radiation coming from the surface of the artifact. When you have an artifact like this one, this is an illumination, a painting in somewhere that is in historical codex or in a book, painting, parchment, all this kind of material are not opaque to the radiation, the visible and the infrared as well. So in this case, the images that you generate are generated by the radiation coming from the sample volume. What is important to stress at the very beginning of this presentation is that in both cases, opaque and non-opaque artifacts, we can get infrared images that display subsurface feature. Even in the case of bronze, for example, radiation cannot reach the element of interest, which is buried beneath the surface, but the heat can do it. So if we cannot display it optically, we can display it thermally. Let's say like this, then I will show you what I mean. And that is the basic principle of thermography. Thermography actually is a little bit more complicated than reflectography, and it is better that I spend some slide to recall the basic principle of thermography and to be more precise of the pulsed thermography. Here, for example, you have a detail of the bronze statue, and the yellow sketch there represents the cross-section of the bronze slab, where eventually it is buried in inhomogeneity. With a pulsed thermography, we have a pulsed lighting of the bronze surface that induces a pulsed heating of the surface. Soon after that, the heat starts diffusing into the sample volume, and eventually it can reach an inhomogeneity, for example, thermal barrier. Correspondingly, at the surface, it is induced a difference in the temperature of the surface locally, reproducing the shape of the inhomogeneities. So we have a sort of temperature distribution at the surface that reflect the elements that are beneath the surface, buried beneath the surface. By means of an infrared camera, I can collect an image of this temperature map, and I can display a lot of things that are beneath the surface. Here, for example, the image is not so clear, but we have hundreds and hundreds of elements like this one, very regular, small rectangles that have been inserted in this bronze after the casting, just to repair the porosity of the bronze and many other defects. Of course, they have been displayed because of the thermal properties of the artifact that I am analyzing. The situation is a little bit different when we have a semi-transparent material, because the light can travel through the sample volume. Eventually, it can reach the buried inhomogeneities, and then what I can collect is a combination of optical and thermal processes. In this case, for example, this is an illumination. The thermograms show two characters aside of the main characters that then have been covered by the blue overpainting that is in this illumination. I will show you something about that later on. So in this case, both optical and thermal properties play the roles. So illuminations, this gives me the opportunity to tell something else about the structure of the semi-transparent artifacts that are usually investigated by infrared imaging. An illumination has a layered structure like the one of a normal painting. Basically, typically, a painting has a cross-section like this, not only like this, much more complicated, but this is the basic one. There is a front medium, which is usually the painting layer. There is a backing that can be, for example, the support, plaster, canvas, wood, whatever. And in between them, sandwiched in between them, often there is the element of interest for us, some underdrawings, a pentimento, what we want to investigate and display with the infrared imaging. This is very well known, very standard, let's say, with the infrared reflectography, and but it is a little bit confined to the investigation of paintings. When I want to see what is beneath the painting layer, and this is an old story, and reflectography can help you in this, but we don't want to be confined to the paintings. For example, we have a completely different artifact here, but the layered structure is similar. We have a front medium that this time is a piece of paper, is a leaf of paper, a backing that can be paper or something else, and a written text sandwiched in between them. That is our element of interest. What is that? That is a picture of an historical book binding. What you see there is the so-called end leaf. The end leaf is that leaf that connecting the book binding to the book block. Half of that leaf is pasted down, is glued on the book binding, and the element of interest that are not optical or mechanically accessible. With the help of infrared thermography, you can detect them, and in this case, you can see also that there is some text written on them, and eventually, if you're lucky, you can even read it. This is possible Usually it is not possible with a reflectographic approach, but we will see this is possible for a number of reasons with the thermographic approach. So I'm trying to tell you that depending on the geometry and the nature of the material, the constituent material of the artifact, you can use one technique or the other one and you can get the information you're looking for. This example gives me the opportunity to recall another capability, which is specifically of the infrared thermography. With pulse thermography, when I record images, I do not record just one image. I record a sequence of images because I remember pulse thermography is an imaging that is performed on an artifact which is out of equilibrium. It is thermally perturbated, and during the relaxation process, essentially is a cooling process, I take and I record a lot of thermograms describing what's going on. Not just one, but a sequence of thermogram. In this example, maybe you can see this is the image, the infrared image of the end leaf, one of the first images of the movie, and you see almost nothing. As time goes on, at a given moment, you start seeing like this, for example, on the left side. I don't know if you can there. Yes, maybe yes. You start seeing a text at a given depth. Then, if you go on, a second text appears that is at a larger depth. So, the larger the time, the larger the depth, you can distinguish at different depths different elements. This is a dynamical way of recording, of inspecting your artifact. It is not a static one. On the contrary, reflectography records single images in condition of equilibrium of your artifact with the environments. Okay, so keep this in mind because I will show you something later on. So when we have reflectography, everything is in equilibrium, and you take one images. Okay, once I've introduced briefly the two main classes of techniques that are used for the infrared imaging, I want to move to the case studies, and I will show you a couple of case studies that concern bronzes, some case studies, but I think a large number of examples of library heritage, that is to say concerning books. And finally, I will show you something that concerns painting and codices. And the case study have been selected because I worked also on them. I know them well. I think, well, the problem that has been faced, and I want to tell you what could be done to solve it. The two cases concerning bronze statues. The first one is really, concerned the capital in She-Wolf. It was a rather famous case study for a number of reasons that I will tell you then. You know, this is the symbol of my city. I'm from Rome. And there is something that I want to tell you about the study of this bronze. The second one is the case of the boxer at rest, and in particular, what was studied in this case was the metallurgical chromatism, how it was possible to get a specific chromatism in the bronze by means of the control of the composition of the bronze. I will show you then something about that. But let me say something about the capital in She-Wolf. What was the matter? There was a dispute on whether it was an Etruscan or a medieval bronze. Okay, from a stylistic point of view, all the art historians say this is an Etruscan bronze. But then when they went to to study the casting process, it seemed to be medieval. There were a lot of other indications that suggested that it could be medieval. The manufacturing process seemed to be medieval. Okay, it was an important matter for us Roman at least, but it is anyway, it's a beautiful statue, and so what was done at the moment was to study in detail the casting process. How could be done? If you want to understand the details of the casting process, you have to study the defects that you find in the bronze and the repairs. That is the first step. And then you can do effectively by means of infrared thermography, and in particular in this case. So you can see this, for example, is a mechanical repair. It is very regular. It is very large. Then I will show you which one was the purpose. But you can characterize it with a thermographic movie, for example. You can see that while the heat diffuses inside the plug, because this is a plug which is mechanically inserted, a light frame is displayed there, and what we see is consistent with a cross-section like this one, when the housing of the plug has a frame step, a support step running all around it, preventing the plug to fall into the empty space of the statue. Okay, so this is so regular, so well projected that you must conclude, and it was the case, that it was planned since from the very beginning, before the casting. The situation is different when you have some repairs like this one. You have a metallurgical repair here, and you can see that it is not regular. It is not regular at all, completely different. It has been obtained with a procedure that is known as a cast-on repair. You have maybe one of you knows the method of the lost wax method. Some wax is applied onto a casting foil. Then you have a clay mold. Then the wax is melted and substituted by the molten bronze. And in the end, you have such a repair. It's a metallurgical repair. It is not a mechanical one, okay? One phase of this repair is a cast, and it is consistent with a cross-section like that one, okay? You see the bronze of the main cast, and the cast-on repair, that is the bronze added in a second step, second phase, as a repair. If you map all of this, you see that in this case, a lot of the cast-on repairs, a lot of the casting folds are in the lower part of the statue. The regular repairs are in the upper part, and this is consistent with a reconstruction of the casting process like this one. This is the armature, and that is the wax model ready for the main cast. You can conclude from this that the casting process was in just single casting. It was made in just one single casting. And that was important because it was mainly the way to work in the medieval age, not in Etruscan age. And that was an information, a very important one. But in addition to that, also many other defects have been mapped. That kinds of defect there actually are fillings of the porosity. This is a patchwork of cast-on repairs. This is a defect that has not been repaired because it's a casting bubble. You cannot see it. It's a bubble beneath the surface. And what was interesting is that there is a very strong concentration of such defects. They were mainly, let me see. Yes, they were mainly concentrated at the same level of the statue. And that was interpreted as the level of the intermediate casting. That was the intermediate casting level. I mean, we have just one casting, a single casting, but which was operated with 2 or more subsequent flows. Just one casting, just one model, and then 2 or more subsequent flows. And the interface between 2 subsequent flows is the region where you find the larger concentration of a certain kind of defect. The other defects are concentrated in the lower part of the statue, the farthest one from the inlet, so the bronze was not in its better condition to reach that area of the statues. But from another point of view, when you have a defect like this one, this is for me an occasion to explain another kind of study that we have done. I was discussing this point before with Professor Franco. All I've shown to you before, it is qualitative. If I want to do some quantitative investigation, very easily, for example, in this case, I want to know how deep is such a defect, its depth, or I want to know the thickness of the bronze. Can I do it with such an infrared imaging? I can do it, but with infrared thermography, you can do a lot of things quantitatively. You can get numbers. The pre-requirements is that you know how rapidly the heat diffuses inside the sample. There is a physical quantity which is called thermal diffusivity. If you know that, you know how rapidly the heat diffuses inside the material. And how can you know it? It strongly depends on the concentration it strongly depends on the composition of the material. And in the history of art, each bronze has its own composition. It is very difficult. You cannot find the thermal diffusivity on an handbook. Okay, you should know the composition, and sometimes it is not enough. So the best thing to do is, can we measure the thermal diffusivity and get a lot of quantitative information? We can do it if we are lucky, and like in this case, the case of the Capitol in She Wharf, there is a part you cannot see very well here, but there is a part of the bronze in correspondence of a casting fault, which is lift. So you have access to both the surface of the bronze. In other words, you know the thickness. If you know the thickness, the length of the path for the heat to travel, and you can determine the time. You know the length, you know the time, you have the speed in some way. You can determine the time, the crossing time for the heat to go from one surface to the opposite one with extracting by the thermographic sequence plots like this one, curves like this one. I promise only 2 or 3, no more than that. Curves like this one. You see, this is substantially the behavior of the temperature as a function of time. And you see that in this log-log plot, it goes down linearly, in a linear fashion, let's say like this. At a given moment, there is a deviation from the linearity. What has happened? The heat reached the opposite surface. So, determining this point, we know the time the heat needs to go to the opposite surface, and we can calculate with an easy formula the thermal diffusivity. Once we know the diffusivity of that specific material, we can reverse the formula and obtain every number concerning the geometry of the statue, the thickness of a given element, the depth of a given defect, and so on. So this is quite important. But not always it is possible to measure the diffusivity. In that case, the B plan is this one. Bronze is a copper alloy containing a certain percentage of tin and lead. And the thermal diffusivity strongly depends on that. This is a curve that shows that if you have pure copper, he is a very good conductor. If you have pure copper, and then you add the 10% of tin lead, or both of them, the thermal diffusivity decreases more than 10 times. It's a huge variation induced by the presence of tin and lead. So this is the value there of the pure copper, and this is the composition, 10%, 15% of tin and lead of historical bronzes. You see, it's much less than that. So if you cannot measure it, but you can determine the composition of the bronze, for example, with methods like, I don't know, X-ray fluorescence, you can understand which one is the percentage of tin and lead, you know, the composition. You can at least estimate the thermal diffusivity, which is needed if you want to do something quantitatively with thermography. And I will show you we could take advantage of this with the next example. This is the story of the boxer at rest. It's a beautiful bronze, in my opinion. And this is a fantastic photograph of the time when it was found in 1885 at the bottom of the Quirinale Hill. Quirinale is the hill in Rome where there is the presidential palace, I think. So you see that during the excavation, they found it there. It seems that he was waiting for somebody to come and to be picked up. So this is where it is today in the National Archaeological Museum of Rome. And of course, this is a Greek bronze. It was found in Rome. It is a Greek bronze. It's a Hellenistic, 2nd or 3rd, probably 3rd century before Christ. And yes, it is not so unusual that in Rome, most of the bronze comes from Greece. During the Roman Empire, they used to bring them to Rome. Technically, they were stolen, let's say. I'm Roman. If there is any Greek here? No, okay. So I'm safe. But anyway, this one has some very astonishing peculiarity that I want to show you. The first one, it concerned the manufacturing process, the cold working, all that kind of work that is done after the casting. I don't know if you can see that. There is maybe a little bit too light here. I can see very well in the monitor. I told you before, beneath the surface, you find small plugs mechanically inserted. They are not longer visible because of the polishing, finishing working, and then even polishing. It was not so unusual to find such repairs in ancient bronze. What is really special in this case, that you can find hundreds and hundreds of them, probably more than 1,000 for sure. They are very small, they are very regular, and they are throughout all the surface of the bronze. It's something incredible, and they are very well hidden beneath the surface and the finishing work. You can see here that with the infrared imaging, you can also see other of such plaques hidden. Some in the middle, there is a casting bubble. You can see also cracks. Maybe those are information useful for the conservators, not only for the art historian, for everybody. And you can even use the infrared techniques to characterize modern restoration like this one. This is a modern restoration of the end of the 19th century. But if you need to know the way they have done it, because it is useful for a conservation point of view, you can do it with such infrared imaging. Okay, this was surprising, but it was not the main focus of the investigation. The main focus of the investigation is this one, the study of the chromatism of the insertions, because in this statue there are a lot of insertions. I will show you then the lips, bruises, because this is a boxer after the fight, bleeding cuts, and many other details that have been colored in some way using different composition of the bronze. And take a look to this. That is almost a reddish copper where it is diluted at 3% of tin. If you increase the concentration, so it's hardly, I would call it bronze, but it's almost bronze. If you increase the concentration to about 10%, it tends to become yellowish. If you increase the concentration up to 20, it tends to be silver-like, gray. If you want to have a much darker gray, you add lead. Not only tin, but lead. And you can get something like this one, if you can see that. Not very well, I'm sorry. But that is a bruise which is at the bottom of the right eye. And it is dark gray because it is plenty of lead. The concentration of lead is 25%. It's a huge concentration. They want to make it darker, gray and darker, differently from the surrounding material, which is still reddish. Okay. Then the same situation is on the broken nose. There is a bleeding cut, and the red of the blood have been rendered with the inlay of pure copper, because the copper is more red than the surrounding material. And this is evident also for the lips. The lips are quite red, and the concentration of tin is very low. So it's incredible how they could control the chromatism by controlling the composition of the different elements of the bronze, and they realized bronzes like this. There is somebody who's still saying that such kind of bronzes probably were colored with some paints over them. There is no reason for that. After such an effort to make them with their own metallurgical chromatism, what's the reason to paint them? There is no reason for that. But you can read a lot about this. What can we do with the infrared imaging? This is a thermography. You see the bruise is very light. And that is because there is a lot of lead. So the thermal diffusivity, it is very low. The heat diffuses lower than in the surrounding material. And then it is light also because of another reason, maybe the main one, because possibly beneath this external outer layer of dark bronze, there is a thermal interface. And that is very important, because if there is a thermal, no, sorry, not a thermal interface, there is an interface which represents a thermal barrier. That is important, because if there is a thermal barrier beneath this element, it means that the element has been inserted mechanically. And the situation is completely different for the lips. The lips in the thermogram are very dark because they cool down more rapidly. They are cold with respect, colder than the surrounding material because they are red, because the copper is much better conductor, and because here this element is thicker. Is there any possibility to establish how thick they are, if they are inserted mechanically or metallurgically? Because a second possibility was that some elements were inserted in the wax model before the casting, and then during the main cast, the fluid, the molten bronze, went in contact with such element, and the contact was very good because it was between a solid part and a liquid part. So what can we study? For example, we can approach the study in this way. That's the typical situation of a mechanical insertion. you have a bad contact, bad mechanical contact that results in a very bad thermal contact. If you have a metallurgical coupling, in this coupling you have a very good contact, mechanically and thermal, and in one case you have a low thermal conductance. I mean, the heat can be easily, not easily cross the interface. If you have a very good thermal contact, the heat can easily cross the interface, diffuses without being hindered. And in that case, maybe you can understand something about the nature of the insertion. Okay, let me show only one more graph, one of the last one. You see, that is a curve similar to the one that I've shown you before, is the decay of the temperature after the heating, is the cooling process. If nothing happened, we have a precise way in which we expect the temperature to decrease linearly. Then something happened at a given time. You see, you have a strong deviation from the linearity that can have different shapes. So if you have a very poor contact, what has happened here? That the heat reaches the thermal barrier and it cannot diffuse any longer. So the temperature goes toward the stationary value. The cooling process stops almost. Not like that, but almost when you have a poor contact. The heat is hindered in its diffusion process. When you have a very good contact, it continues going down linearly until it reaches the opposite surface of the double layer. Okay? So in this case, with this kind of analysis, we can understand, depending on the curve that we can extract from the infrared thermographic sequence, if the insertion was mechanical or if the insertion was metallurgical, for example. We have done it in our case, in our examples, and what can you see is this, that as far as concerns the bruise beneath the eye, you have a deviation which is quite strong, and you can conclude that it has been applied after the cast. By the way, by the study with some model of the experimental data collected, we can also determine the thickness of this layer and the conductance of the interface. So something which is quantitative. As far as it concerns the lips of the boxer, you see it goes down with a very small deviation. So in this case, we can conclude what was expected, that the lips were coupled to the bronze of the main cast during the cast. They were included in the wax model and coupled during the cast. In this case, the thickness was, minimum thickness was 6 millimeters, so very thick to be an element in a bronze statue. And the conductance was very, very high in this simulation. Let's move to another kind of artifact, completely different, another field of the cultural heritage, the library heritage. And I will show you another kind of problem concerning what I have shown you before, the possibility to detect, characterize, and eventually read some hidden text in the book binding of historical books without dismantle them. This is the point. You see that with thermography, in that examples, there is a text which is clearly detected, and then we will talk about that. And then I will show you some information that we can get studying illuminations in ancient books. In particular, the metastructure, the one that is beneath and it cannot be reached, that is beneath the outer layers of the illuminations. But let me go more in detail with the first problem. Okay, this is if there is some of you which is not familiar with the book binding of old books, This is a dismantled book binding, and you see one element of interest for us is the spine lining. In the spine there is a leaf that is used as a lining of the spine that eventually it can extend over the edge, and the part over the edge is called wing. Okay, wing of that book binding. And as you see in this image, most of the time such material was reused material. It was taken in the archives, in the library where the book bindings were made. And on this material, often, very often, you find earlier texts of earlier age, and most of the time are much more interesting for the scholar, for the paleographer, this kind of text here with respect to the, I don't know, the text of the book itself. So it should be a good help, the possibility to read them without dismantle them, okay? Without dismantle, not them, without dismantle the book binding and the book, of course. But unfortunately, they cannot be read because they cannot be read because they are sandwiched in between the end leaf of the book binding and the book binding itself. So, can thermography show them? I've already shown you that that is possible. There's a written text on the wings of this book binding here. You cannot see it, you only see the end leaf, but you have the text there that can be, in this case, maybe even read. There is an uncountable number in the historical library of Rome, but I think all over the world, of books that contain such written scraps used to structure properly the book binding, because it was a common practice to rebind the books in the 16th, in the 17th, and even in the 18th century. So we can often find something like this one, where you're lucky, you can even read some of this text, but not only the wings, often also the board lining is written, and so you have extended part beneath the end leaf that are written. It's very easy to detect them with the infrared thermography. It is more difficult to characterize them, and the challenge is to read them. So the real problem is the readability of such text. Why I'm underlying this? Because this is not a kind of optical reading. This is a thermal reading. The contrast image that you have here, it's a thermal image. It's a thermal contrast. When you see something lighter than the rest, it means that it is hotter than the rest. The black part is the colder part. The white part is the hotter part. Okay, this is a thermal contrast. You are doing a thermal reading, and thermal reading is affected, the thermal readability is affected by specific parameter. I want to show you them with an example. Here there was a lucky case. The text was very close to the surface. So immediately after the onset of the flash, immediately after the thermal perturbation, the light could reach easily the text, was selectively absorbed by the black ink with respect to the non-black surrounding area. So we immediately have a difference of temperature there, a contrast, a thermally contrasted image, and we can get a very good image because it was very close to the surface, very well coupled to the outer foil, and it was very clear. But what happens if I wait a little bit longer? I mean, if I pick up a thermogram at larger delay, if I wait a little bit longer, you see what happens there? And if I wait still longer, you see nothing. There is a blurring. What is this kind of effect? It is due to the fact that the heat diffuses laterally. If you don't let him diffuse laterally, you don't have this kind of disturb. If you wait too much, the contrast, you see, decreases, and the sharpness of the text is lost. This happens because, I told you, suppose this is a sketch, this is a cross-section in the sketch, this should be the ink, this is the paper. If the process is very fast, you only consider the one-dimensional heat diffusion. Actually, there is also a lateral diffusion due to the fact that here the heat is absorbed much better than here, so there is a thermal gradient. But in this case, the process is so fast that that is negligible. And you have a profile of the signal like this one, where there is the ink, the light is absorbed, it is selectively heated, and you have a large signal. When there is no ink, the light goes through, and okay, this one is colder, and you have a profile of the signal like that, and it results in a very clear image. By the way, the difference of the signal that you have here is what we call contrast, okay? Simplified version of the contrast. But if we have a long time, we wait for too much long time, we have this disturb because we give time to the heat to diffuse laterally. And this kind of diffusion, this kind of diffusion results in a smearing, in a broadening, in affecting the sharpness of the step-like profile that I've shown you before. And you can even quantify this area, the extension of the distortion. You can define a parameter which is the distortion index that accounts for these. So if you take together contrast and distortion, you know that those are very crucial parameters to consider when you want to read thermally something which is hidden beneath paper, for example. The last one, I show you again the same movie than before. Now maybe it is clearer what happens. At the beginning, you see nothing, then the first text appears, and then a larger delay, you see also the deeper one. So the larger the time, the larger the depth. If you have a text, an element of interest, which is too deep, it is very difficult to have a clear image of it. So actually, the best readability depends also by the nature of the elements you want to investigate. Those are the last two plots. You could do this. You say, I have to wait for the maximum contrast. That is okay. But if I wait too much, I have the distortion that probably affect the readability. So what can I do? Of course, for the best readability, you should find the best compromise. There is no chance. It depends on the depth where the text to read is. Remember, this is a thermal reading, so it's affected by thermal phenomena. Okay, let's move in another completely different situation. This is an illumination of an illuminated manuscript of the 14th century, the Liber Regulae Sancti Spiritus in Saxia. It's a very famous one because it is the first codex where it is stated the rules of the modern hospitals, which kind of assistance had to be yes, this is the Sancti Spiritus. It's an ecclesiastic order that at the very beginning has this kind of mission, the assistance of the poor and people that couldn't access to hospitals and the structure where. So hospitals, it is explained here. Sorry, I was thinking to something else. Okay, This was a copy that was destined to the Pope, so this is a very rich codex. It has plenty of illuminations, plenty of rich materials, lapis lazuli, a lot of gildings and things like that. And I want to show you that by means of thermography, you can display elements that are sometimes displayed also by the reflectography, sometimes are complementary. For example, in each illumination you find something which can be interesting. In this case, you have a red background, and you can see in the upper part that actually it was an overpainted part of the illumination where there is some architectural elements, a window and stair, or things like that. This one was the one that I've shown you before. There is a preceptor with two characters aside that you cannot see here, but you cannot see in the thermograms there. By the way, in the following pages, there is this illumination, and those two characters are there, so probably the miniaturist made a mistake, represented them in the wrong illumination, and then covered them and make them again in the right one. Then if you go and take a look, for example, to the other figure, the other character that is there, you can find a small table with a jug, with something that is covered again with a blue paint. Every illumination is rich of indications of concerning the manufacturing. In this case, this is a real, as it's called, pentimento, change of mind of the author. The two monks are fighting, and this is a previous rendering of the legs, feet, arms, and whatever. With thermography, in addition to what you can see also sometimes with reflectography, you can get, you can recover, for example, the readability of some graphic elements, like that one, the texture which is on the drapes behind the character, or you can detect particular materials. When we think to the gildings, we think that the gildings are the outer part of an illumination. In this case, for example, it is not. You see the red drape there. If you look at from the original, you say that it is shining in different points. And that because beneath the red paint, there are two gold foils, and then they have been scratched in a specific way to give the idea of something that is shining. So that is really something qualitative that can be done. But what I have shown those images to you just to let you see that sometimes with thermography you can collect informations that are complementary with respect to the infrared images that you can get with reflectography. Now I want to show you something else concerning, let's say, the recent developments of the infrared, the most recent developments of the infrared imaging, consisting in combining the two techniques in different situations. And I will show you with the investigation of a painting which is preserved in Santa Maria in Cosme in Rome. And then I will tell you something about the possibility to get a three-dimensional infrared rendering, I mean a three-dimensional model, digital model, of course, of your artifact, with the appearance of the infrared thermography, so a sort of 3D thermography. I will tell you something about that. First, I want to recall this point. Now I told you something about thermography. You know that there is some light going onto the sample, the heat diffuses, and then you can generate the image by collecting the emitted infrared radiation. And that is usually done in specific ranges of the infrared spectrum. In particular, the most common one is the mid-wavelength infrared part of the spectrum. reflectography, most commonly, it is performed in very close to the visible spectrum in the near infrared, but you can reproduce the same mechanism in different part of the infrared spectrum with an approach that we call multispectral approach. So when you do this with the reflectography in different ranges of the spectrum, you display different elements with the same technique in different ranges. Among these ranges, one of them could be the one where thermography works and then provides you with a huge advantage, a big advantage. Because in that case, if you try to do thermography exactly when you do reflectography, you have to detect the same kind of infrared radiation, and then you can use the same detector, the same infrared camera. And this is a very important advantage in some application. Let me show you here what can you do when you do simultaneously infrared reflectography in different ranges of the infrared spectrum. You see, this is in the near infrared, this is in the mid wavelength, the infrared, and you see that the two images are quite different. They display different details. I could say that this one is a little bit more superficial. This one comes from a deeper layer, partly. I will show you them. Or otherwise, you can do with the same infrared camera simultaneously the reflectography and the thermography, two different techniques in the same range of the spectrum. And also in this case, with the same, simultaneously, with the same device, you can get reflectograms and thermograms. Thermograms, you see, are quite different. You can compare them to see if in this way we can get different information. For example, look at this one. This is a thermogram. The appearance is the one that you have in the visible region, but superimposed to them, you have a lot of details like that one, defect, repairs that have been done beneath the external, the outer painting layer. Thermography can consider a relatively large layer from where the informations come. With the reflectogram, only the most superficial layer of the paint is investigated. What you see there, for example, are those parts, are retouches that have been done before the last restoration, probably. And then you can see also probably this part. If you compare the two, you see that this is a devotional painting, and probably that was an hypothesis. It was overpainted, and I think that this comparison in between those images suggests that it has been overpainted. You see, the style is quite different. Okay, let me show you only this last to conclude. We tried to do some infrared, three-dimensional infrared imaging on some beautiful illuminated manuscripts preserved in the Angelica Library in Rome. But the problem is that to do some three-dimensional thermographic imaging, it is impossible directly from the thermographic images, because I told you before, the thermographic images have been collected in condition of out of equilibrium. You need different points of view, and you will never reproduce them, the same situation from different angles. In this case, it could be done because of the reflectographic images. We used the reflectographic images to get a 3D reconstruction, and then the device was the same. You have a correspondence pixel by pixel, and you could transform your 3D reflectographic image in a 3D thermography. Then, once you do this, you can implement it and combine it even with the normal 3D modeling, and combine all of them. And to conclude, I show you the results of a recent project that we have done, where we combine the normal 3D reconstruction, the digital 3D reconstruction, with the 3D thermography. And you can get something like this, where you have the possibility to, of course, to explore your digital reproduction of the manuscript. You see this part here, the gray circle is a sort of infrared lens that, if you want, it enables you to see what is beneath the surface. Okay? For example, let me show you this. You see you have different depth here displayed. Okay? And, it gets stuck. So probably this is an indication that I had to conclude. Sorry. I was here. And I'm going to conclude. Okay, I wanted just to show you this. But I can't. For example, look at this. The character at the left side, which is on his knee, okay, he has an uncovered head, you see? But in the previous version, if you look, there was a hat on it. It was looking at a child, Jesus' child, and probably it was necessary to remove the hat. I don't know what has happened, but okay, with this movie, everything was concluded. So let me jump to the conclusion. I don't know what has happened. I will discover. Okay. Conclusion and perspectives. With the infrared imaging, we could do a lot of things concerning the imaging of the elements that are buried beneath the surface. And I showed you, for example, the example of the thermal reading. And as a perspective, if you want to read something that is not properly readable easily, I can imagine that a great help will come from the artificial intelligence to do that. I've shown you that it is possible, differently from many other imaging techniques with the thermography, to do some quantitative investigation. Thermal diffusivity can be measured, conductance of the interfaces, the depth, contrast, distortion of the images, many things. And finally, if it was very difficult to think to a three-dimensional thermography, now it is possible, because it is possible to combine it, which is to combine it with a reflectography acquisitions, and to do whatever you like in terms of exploration of a 3D digital model that can be explored in some way along a fourth dimension, because you have a three-dimensional reproduction of your object. You can rotate it because you have three space dimensions, but then you can fix a point of view and you can do some depth profiling analysis. You can investigate the direction of the depth. And that is all, and thank you for your attention. That's all.
Professor, thank you very much for this extraordinary exploration of cultural heritage through the eyes, or better, through the lens of infrared radiation. It's really a sort of hidden dimension of heritage that speaks about history, about us, about craftsmanship. I mean, it was very impressive for me. So we have here many members of laboratories, from scientists, not only from physics, from chemistry, and maybe there are some more technical questions before I ask more general question. Are there any questions from laboratories? I mean, yeah, great.
Hi, thanks for the very interesting presentation.
Thank you.
I wanted to ask if you have any limitations in terms of damaging.
Sorry, I can hear well. Yeah?
I wanted to ask you if you have any limitations in terms of samples and damaging the sample. Do you have any limitation on, for example, how many times you can analyze a surface or anything like that?
Yes, I mean, you mean some laboratory samples that investigated before apply these techniques to the original one to understand how long it takes for some... Okay, to avoid to damage your sample in that sense. Yes, of course, I didn't tell you about this, but this was the crucial point. Before developing any kind of this technique, you had to study it carefully, because it is classified, this kind of imaging, in the category of the non-destructive techniques. It is a non-contact technique. So you can think that this is absolutely not invasive. That is not true, of course, because we have an exchange of radiation, and that means an exchange of energy. And if you chemists, you know quite well that if you supply your material with an amount of energy which is high enough, I can activate a lot of reaction, chemical reaction, and so on. So we have to control very carefully the amount of energy that is incident on your sample, and we test it in the lab. We use a lot of filters to remove the unnecessary radiations, and we can play with the distance. We have a lot of tricks to avoid to damage the sample. Sometimes you cannot measure them, and that's all. It is not a tragedy. If you have to preserve it, and you understand that the amount of energy could be too much, for example, for a very old piece of paper or for a pigment, and you do not do it. It is not usually a problem with bronzes, of course. It is much more critical with illuminations, for example.
Thank you. This is a meaningful, really, discussion, because conservation deals with delicate, irreproducible elements. So how we deal with them, even when it comes to buildings, I mean, it's complete another way of doing, less muscular, more delicate, where ethical dimension is as much as important as the, let's say, curiosity of analysis.
Yes.
Are there any other questions? Yes? Blaž.
Thank you. I got another technical question. So you illuminate it continuously, or you have like the flashes? And how fast is also the camera? So frames per second, or you're recording in the movie and then extract it, or it's just the pictures?
In the configuration I've shown you before, you have a pulsed heating. So only flash lamps, by absorption of the light, you have a pulsed heating. This is only one of the many possible configurations of thermography. Another very popular one is a continuous periodical illumination, the so-called lock-in thermography. You can do it with an illumination which is continuous but modulated. Okay. Then there is other kinds of stimulation, like step cooling or step heating or whatever. In this kind of configuration, the pulse thermography, the duration of a sequence, it depends on the thermal properties of the sample, but runs from, let's say, 1 second up to 3 seconds. And you collect a frame every 10 milliseconds, more or less. And concerning the invasivity, it depending on the absorption properties of the material, but you can induce heating or that runs from 1 Kelvin up to 20 Kelvin, for example. If I have to measure something in a bronze statue, I need a lot of power, and it is safe, because that is bronze. If you send light on bronze, it is not a big problem. I cannot do it, again, I cannot do it on an illumination or other very sensitive material. But yeah, the time it takes is more or less a few seconds. The processing of the images, that is quite long, especially if you want to do something quantitatively. I don't know if I...
Okay, then I will have also one question, more general. Now, we are deeply in heritage sciences here, and I'm interested in your team, how many other colleagues from other disciplines are there? What is the interdisciplinary dimension of your work? How much you're able to really not be separated within your discipline and really interact for the purposes of the outcome? And finally, another question. I mean, you come from the field of physics, and the passion for your method is evident, but the passion for heritage is even more evident. So when you decided to deal with heritage sciences and with the heritage?
A long time ago. Okay, I will tell you then. Let's start with the first question. Yes, my research group, for example, I'm a physicist. There is another physicist. There is an engineer. The most active in the group is an art historian. She studied conservation of cultural heritage, master in art historian, PhD in industrial engineering, developing diagnostic method for cultural heritage. And how is such a group interdisciplinary? It is essentially interdisciplinary. I was telling to you before that to me it's very important to work not in a sectorial way, but to work together, because I can increase the awareness for the artifact, the knowledge of the artifact. In one word, I can increase my sensibility for the artifact. If I do not work, if I work in my lab and I do only physical measurements, I will never understand what I'm doing. What I tell to my students in the curriculum of preservation of cultural heritage, I say, I'm a physics, never trust physics, stay there during the measurement and interact with them. It is true also the reverse to me. I like it very much. I like to work with people from other fields because you have an exchange. You always maintain your proper skills and capabilities. I think I will be always ignorant as far as it concerns art history, but I like it. And I like to work with that. Since when? 30 years ago, I had the opportunity, I was just after the degree, they were making the copy of the Marco Aurelio statue in the Capitoline Hill in Rome until the 90s. There was the original, then the original was restored, and they made a copy. And at that time, somebody called me and a colleague of mine to check the quality of the bronze of the copy, and I spent half a month inside the statue, because when they had to restore it, the knife was removed from the horse. And so you could access, that was quite exceptional, inside that statue. And I started at the time to interact with restorers, art historian, and I had some doubt about my choice. Okay.
Thank you very much. Well, with this, I hope... Oh, there is another question. I don't know if Andrea will allow that we have this last question.
Once again, thanks for the presentation. Previously, you answered that there are some samples that are too sensitive to be interacted.
Radiation, yes.
Is there a chance that in the future there will be some technological advancements that will make them not too sensitive? And if so, how do you think that might be achieved?
Of course, there are chances. Always there is always one more chance. Let me give you this example. There is a lot of X-ray exploration of cultural heritage because it is considered a non-invasive technique. But if you think in a different frame concerning, for example, our health, you go in a hospital, they do a radiography, and I remember that 30 years ago, it was really, really dangerous. Now the dose, I mean, okay, the intensity of the radiation is much, much smaller because the sensitivity of the detector is much, much higher. So technology can develop sensors that are always, more and more sensitive and requires an invasivity which is smaller. And another example that I can tell you, for example, maybe you know the case of the burned papyrus from Ercolano. You know, there's the problem to read what is inside. Many, many years ago, they started to do something, and the outer part was thrown away because it was black. It's impossible to read it. So they tried to unroll them and to read what was inside, throwing away the outer part because it was not possible to read it. With some infrared imaging and with some UV reflection techniques now, you can read it. So what was not possible a few decades ago, it is possible now. And so I think that in perspective, what you cannot see now, you can do probably in, I don't know how many years, it depends.
Thank you so much. I'm afraid we have to conclude. And I hope that this lecture will inspire many young researchers from physics, chemistry to join and explore the beautiful world of cultural heritage, because only we understand our past, we can predict our future. So with this, I invite you to join us downstairs for a glass of wine. Thank you very much for your attention.
Thank you.